Good morning. Now, let me make it one thing very clear. So far, the type of binders I have talked of are water soluble. One of the biggest problems of fabrication and processing of ceramics is that there are some systems, like say if you want to make a barium titanate capacitor, it is preferable you use a non-aqueous solvent, because in aqueous media the barium titanate would hydrolyze. The finer the grain, the faster it would hydrolyze. Organic solvents used in ceramic processing include acetone, MEK or methyl, ethyl, ketone, alcohols, mostly methyl alcohol, MEOH, ethyl alcohol, isopropyl alcohol. These are used. In certain cases, furan is used. However, one of the biggest problems that ceramic industry, one of the difficult issues ceramic industry has to tackle is how to deal with the waste solvents, because these are environmental hazards. Hence, even though today many of these solvents are in use in ceramics processing, yet attempts are being made to phase them out. Now, whatever binder is used in aqueous system may not be good enough in non-aqueous system. Whenever I talk of non-aqueous system, I will be talking of the binders which are good for non-aqueous system. But for the time being, because the world effort is to shift more and more to aqueous system to address environmental concerns, I shall be talking principally of additives in aqueous media. Whenever I have to go to non-aqueous media, I shall tell you what are the types of additives which are used in non-aqueous media. Before I carry on with what I said, a brief recap. Yesterday I covered some binders, examples of binders in aqueous systems. If I talk of inorganic ones, I have clay, including bentonite clay. I have magnesium, aluminium, silicates. I have soluble silicates. There is sodium silicate. You will see later I shall be using colloidal silica as a binder. I shall use colloidal alumina as a binder. Phosphates. Now this phosphate is something that is banned under Montreal Protocol. Of 1995. Phosphate had been used extensively, not only as binder but additives in food. The soaps we use principally had phosphates. It is now banned, though industry in India, which is not that well monitored, is still using phosphates, especially metaphosphates and borophosphates. These are the two which are being used by many industries in India, in spite of the fact that it is a banned item. There is a worldwide ban. Today your soaps do not contain any phosphates. Food additives do not have phosphates, but it's still happening. These are examples of inorganic binders. The organic binder list is obviously huge, so I shall deal with again with certain classes. PVA stays on the top of my list. I'll tell you why little more. But one of the biggest things is, two reasons, is that it is clean burning. So when the ceramic material is fired, it burns cleanly, leaving no carbon. That's one advantage. The second advantage is the glass transition temperature can be changed. I talked of this briefly yesterday and I shall again talk of it today. Then is petroleum waxes. Then comes cellulose, resins, both thermosetting and thermoplastic. Alginates is a very important one. Sodium alginate, lignin, paper industry waste is a very important one. Gums of selected grade are very important. Starches, flours, casein, gelatin, albumin. Albumin is the egg white. Proteins, acrylics, they are all excellent organic binders which are compatible with aqueous media. So, having talked of binders, let me again briefly go on to say why polyvinyl alcohol is a favorite of mine as a binder. So, I will recap an example of yesterday. Yesterday I talked of biaxial pressing, where I had a die this is the anvil, the powder and the ram. This is the support table. So, the ram moves down, keeping on going down till it reaches a thickness where further compression is impossible and all the powders are compacted over here. It is the powder plus the binder. Now, to give you an example, real life example, if I am using a 13 millimeter die and I take say 5 gram of alumina, I will add to it 2 drops of 10% PVA in aqueous media. Mix and then fill in die and then press. Now, I pressed it, I press the powder, and now I want to take the pellet out. So, the first thing that I will do is now remove this force and raise this platen. So, what will happen? A stage will come when this is the pressed binder that you have done over here. This is the anvil on the platen which is moving up. Now, let us focus on this area as to what happens next. So, this is the die. Powder is here. The anvil is being pushed up. Let me magnify this many more times. Wrong. The powder is over here. Now, what I have done now is I pushed the anvil up so that this press pellet has moved up. Now, over here in this particular situation, what was the stress distribution in this pellet? In this pellet, the stress distribution was something like this. So, this powder was contained on three sides. These are the die walls and there is the anvil. But once it comes over here, it will tend to release the stress. And what will happen? It will expand. And as a result, what happens is this breaks off, leading to end capping. Why does this happen? Because the polymer expands. What happens is something like this. Press, it goes down, keep holding it, and then release. This is press cycle, and this is pressure release. What would happen? This would immediately bound back. It may go back to the same place, or it may go back to a lesser height. But yet, this is rebound, which leads to this expansion. Now, in pressing the pellets, we certainly don't want this. What is it that we want? We want something like this. Deformation, time. This is the pressing cycle. We want only a small rebound. The rebound here is much lesser than the rebound here. What we desire really is this type of happening where the rebound is much smaller than what it is over here. Now, polyvinyl alcohol that is used as a binder, PVA, molecular weight roughly 1,44,000, which is available in India. It has a TG of around 65 degrees C. So, it is obvious this PVA would rebound as in here, and this rebound is simply unacceptable. So, what is done is to convert the PVA so that this TG is closer to room temperature. Additives like polyethylene glycol, molecular weight say 20,000 is added to PVA. The PVA, the PEG acts as plasticizer to PVA, means it causes PVA chain breaking, which leads to lower molecular weight PVA, which in turn leads to decreasing gas transition temperature. So, with the binder like say PVA, which is ideal for ceramic processing because it is clean burning, we add plasticizers like PEG, which cause chain scission of the PVA and reduce the TG, so that the rebound is now very small. And this is done with PVA plus PEG acting as the plasticizer. So, in here what I have done is we have changed the character of the binder, which is a very desirable binder like say PVA, so that it can be used in pressing of ceramics of shape forming without the sample being destroyed due to internal stresses, and we do not have any other way. This is, with this I stop talking of binders for the time being, and now move over to another one, which is lubricants and compaction aids. In ceramic processing. You see, in most cases in industrial ceramic production, we strive to have spherical ceramic powders so that the packing or the green shape can be improved. But frequently we do not seem to get totally spherical powders, and most of the powders that are used in ceramic processing have jagged sides. They have got more than 5, 6, 7, 8 sides and all of that. So, when I have put the powder in the die for processing and I am pressing it, the powders which do not have a smooth surface or have a rough surface may well prevent optimal packing of the ceramic. And as a result, I have a more porous green body. Now, this is one problem. The other problem is, which I did talk of when I was talking about the stress distribution. When I am pressing the powder, from the hammer comes down from here to here, there is a huge friction on the side walls, because the powder is coming down. If I am forcing it down the die, that powder is trying to expand in the lateral direction, but is confined by the die walls, and so there is a huge strain on the sides. Just do a mental calculation. This is a 13 mm die. This is the anvil. This is the anvil, or rather, sorry. This is the hammer. $13mm. I am applying, let us say, 1000 kilograms load here. This is a 13 mm die. Calculate the load on surface and calculate the load on die wall. Please remember, this is a force per unit area. On the surface, I have 13 millimeter. So, the surface area, you know how to calculate. I will not deliberately calculate. And this one is hardly 3 millimeter. This height is hardly 3 millimeter. So, calculate the load on this die wall. It will be very, very, very high, very high. And we all frequently have to see that the die wall friction is minimized. Why? If the die wall friction is not minimized, what would happen? Stress, that is over here, the stress distribution would be non-uniform. So, that is why I said I have to talk of lubricants and compaction aids. Lubricant and compaction aids. Lubricant for two things, so that the die wall friction can be minimized, the particle to particle friction can be minimized, and the compaction aids, so the particles can slide, so that we have a higher green density than what we had. Among the lubricants and the compaction aid, the most common one is stearic acid, all we do is we prepare a solution 5% in water, and then before pressing apply this with a cotton gauze or a tissue paper on the die walls and press. This is one of the most best, cheapest lubricants against die wall friction. Synthetic waxes are also excellent die wall friction reducer. The third one is zinc stearate. Now, let us see how they each perform. Let us say this is the ejection pressure. It means that when the anvil is moving up and the situation has come to this and there is no hammer there, in that case when I am trying to eject the pellet, that is the ejection pressure on the anvil, and this is the lubricant percent. So 0.1, 0.2, 3, 0.4. This is the lubricant percent, and the ejection pressure in kilogram. Let us say put numbers for ease of understanding. This is the ejection pressure, units is kg. Stearic acid would behave this way. Synthetic wax would be something like this, and zinc stearate would be something like this. What it means is very simple, that if you are using zinc stearate, you can use much lower ejection pressures than you need to with stearic acid. Let me give you some examples of lubricants before I move on. I have said zinc stearate, that is a very good one. Stearic acid, oleic acid, naphthenic acid, the next one is a hugely important one, boron nitride, especially if pressing is done at an elevated temperature, graphite, and I have already stated paraffin, synthetic wax, stearates of lithium, magnesium, sodium, etc., and talc. Talc is the powder that you use. Uh, so these are the lubricants which are used in die pressing. Other than die pressing, that means you are not making calper tablet. Suppose you want to fabricate, let's say, a jug, or even the wash basin that you use in which you wash your face in the morning, or the commode which is possibly where you head to as soon as you wake up. The other things, there are a lot more other things that need to be added if in those particular systems. Like say, I would say expand the list now. I've already said binder. This increases the green strength. Green means unfired body strength of the ceramics. I've already talked of lubricants which are needed for mold release, die wall friction decrease, and all that. I've already talked of compaction aids. Which cause particle rearrangement and higher green density. I've talked of all of these three. Oh, I've also talked of plasticizers. This also I've talked of. Now, when I'm talking of say manufacturing a commode or the wash basin, you will see later that it is made from a suspension of the ceramic powders in water. First, if I am talking of that, then the basic process is called slip casting. Though this is not the point at which I will deal with slip casting in detail now, but now a stage has come where we talk about the other types of binders which are used in ceramic systems. What is done is there is a porous ceramic mold made from plaster of Paris. I will come back to this again, but this is an elementary introduction. This is first filled with the slurry It is 1. Fill mold with slurry. 2. Let stand. What happens when it is allowed to stand? The water from the slurry gets driven into the mold. Because it is made of plaster of Paris, which does not have any water, the water would drive itself into the mold, causing deposition of the powders which was there in the water, which has moved out over here. So, as more water moves out, what do you expect to gain? A thicker coating on all sides. After a predetermined time, what we have is the thickness of the coating that we desire. The lots of water have gone into the mold. So, we have got a slurry which is powder which is sticking to the walls of the mold and slurry. This whole thing is then inverted. Excess slurry poured out. Now, what we have is the mold with the excess slurry gone. I have taken the mold, poured the slurry out and made it again. So, I do not have the excess slurry, I have the mold over here with the slurry forming a coating on the mold, coating thickness depending on the time it stood over there. Let dry. So, now the issue is we have to take this mold, pour the slurry in and let the slurry stand here. This slurry is allowed to stand at times 2 hours, 12 hours, 24 hours, depending on the thickness we need. During this entire period, when the slurry is standing inside the mold, it is absolutely imperative that the density of the slurry remains constant. Please understand, it is not the powder only going out, but the liquid is also going out. So, we need a very, very stable suspension which would keep the powders over here afloat for 24, 48, 96 hours. So, here now I am coming to a zone where I have to talk of not binders only, but additives which would stabilize the slurry. So, here we are going to deal with a wide range of additives, with a very wide range of additives, like say deflocculant, whose purpose will be to control surface charge, allow dispersion, avoid coagulation. That's one. Then wetting agent. What is it? This is simply something that reduces surface tension so that the surface is wetted. Anti-foaming agent. This will prevent bubble formation. At times we add sintering aids. Sintering aids. We also add at times dopants, stabilizers, and a lot of other things. So, here in ceramic systems, we use a wide variety of additives so that the material can be fabricated and shaped. Now, let me first start with surfactants. Or what I had written, deflocculants. You see, surfactants, big name. Nah. The washing powder that you use for washing your clothes, Surf Excel, is a surfactant. Its beauty is that a surfactant has a long chain, and on one end is a large molecular group. This end attaches to the particle and this end to the aqueous media. So, what happens is this, that these surfactants, it attaches a water molecule to the pellet. So, this will keep floating. What we will have is, if we have got an beaker, if you have a beaker and you have got a suspension and you add a surfactant to it, what will happen is the surfactant will push this way up and the ceramic particle will be separated. So, what we can have is ceramic particles which were formerly a loose compact, they are now very well dispersed. The advantage of these surfactants is you can make this group plus, this group minus, or you can make this group minus and make this group plus. So, one is a hydrophobic one is a hydrophilic one. Examples of surfactants are many. For example, anionic surfactants are sodium stearate, another one would be cationic, would be dodecyl, trimethyl ammonium chloride. There are non-ionic ones also, like ethoxylated nonyl phenol. Each of them are used in their own areas depending on what material you are choosing, and you can choose from any of these surfactants. I shall carry on with these additives in the next lecture.